Section: Introduction. In this section, we introduce the concept of large language models, LLMs, and their advancements in natural language processing, NLP. We recognize that while LLMs excel at generalizing across various tasks, they are not suitable for all situations, especially on small devices like IoT devices or smartphones due to their resource demands. Privacy concerns also limit the use of LLMs in applications like personal conversational AI, as user data must remain on personal devices or private networks. We note that traditional fine-tuning of LLMs involves centralizing data from user interactions, which raises privacy issues. In contrast, federated learning, FL, allows for collaborative learning while keeping user data private by training localized models on client devices. However, Florida does not address the high costs associated with inference in LLMs. To tackle this, we turn to small language models, SLMs, which are more efficient but may lack the robustness and generalization capabilities of LLMs. SLMs also face limitations in composability, forcing a choice between efficiency and robustness. To address these challenges, we propose language model building blocks, LEGO, a flexible, model-agnostic approach for federating SLMs with various architectures. LEGO enables efficient fine-tuning and inference while maintaining privacy and optimizing performance across different resource constraints. By treating SLMs as building blocks, we can reconstruct an LLM from them, allowing for a wider range of client devices. Our experiments show that SLMs, when used with LEGO, perform better as learners and adapt more effectively to diverse data. The key contributions of our work include a method for composing SLMs into a robust LLM, a privacy-preserving Florida architecture for heterogeneous SLMs, and optimization techniques for client-side SLMs based on varying resource budgets. We outline the structure of the paper, starting with background information, followed by the methodology of the LEGO approach, experimental results, related work, and concluding with our study's limitations. Section Summary. In this section, we introduce LEGO, a model-agnostic technique that federates small language models, SLMs, to enhance privacy, efficiency, and adaptability in distributed conversational AI systems. By treating SLMs as composable building blocks, LEGO allows for flexible fine-tuning and inference across diverse client devices, ultimately enabling the reconstruction of robust and generalizable large language models, LLMs. Section: Methodology. In this section, we present our methodology for an efficient fine-tuning and inference system tailored for private and resource-limited environments, which we call LEGO. Similar to how we stack small building blocks to form a larger structure, we combine small language models, SLMs, to create a more powerful large language model, LLM. Our approach consists of two main steps. First, we generate SLMs of various sizes by pruning a larger LLM. Next, we implement these SLMs in a federated learning (FL) setting, ultimately merging them back into a single LLM. The SLMs we create through pruning serve as local models for clients in the Florida environment, and we design them to fit the different computational capabilities of client devices. We use a full-sized LLM as our global model, meaning each client model is a smaller part of this global model. To fine-tune the LLM using the client SLMs, we initiate federated fine-tuning. In each round, selected client SLMs are fine-tuned on their local data, and then we combine their updates to form a global update. This global update is applied to all client SLMs and the global LLM. We repeat this process for each round of FL, resulting in a well-tuned LLM built from the contributions of the client SLMs. For our experiments, we set specific conditions. We use LoRa for fine-tuning, which makes the process more efficient while maintaining model sparsity. We provide additional configuration details in the appendix. All aggregation is done over the LoRa adapters, which helps reduce communication costs. We fine-tune using the Databricks DALI 15K dataset or its subsets, which covers various capability domains. In our experiments, we simulate an Florida system on our cluster and explore 4 levels of model sparsity. 0%, 25%, 50%, and 75%, indicating the amount of weights removed. We utilize sparse GPT to achieve the desired sparsity in a Llama 7B LLM and find that sparse GPT outperforms other pruning methods like Wanda and layer pruning. We create a model-agnostic Florida environment that allows us to aggregate different-sized SLMs into a global LLM. At the end of the Florida process, we obtain a fine-tuned global LLM from the aggregated SLMs. Our algorithm details how clients are assigned their respective SLMs with specific sparsity levels. During training, clients fine-tune their LoRa adapters on local data from the Databricks DALI 15K dataset. After fine-tuning, we aggregate the LoRa adapters from selected clients to form a global update using our heat ag method, which is our strategy for heterogeneous model aggregation. In our heat ag approach, we start with a global LLM to hold the final global update, which we create by aggregating the client SLMs. We access each client's LoRa adapters and create a mask based on their sparsity. This mask is then combined with the global LLM's LoRa adapter wherever there is overlap. By focusing on the non-zero parameters, we maintain the sparsity of the client models while updating the global model. This aggregation process occurs for each client, leading to a global update that we can apply back to each client using the same method. The result is that we effectively average the parameters only when there is a match, ensuring that the updated global adapter retains its structure. Section Summary. In this section, we propose LEGO, a model-agnostic federated learning system that efficiently fine-tunes and aggregates small language models, SLMs, into a robust large language model, LLM, by utilizing a two-step process of pruning and federated fine-tuning. We implement a heterogeneous aggregation method, heat ag, to combine updates from client SLMs while preserving model sparsity, ultimately creating a fine-tuned global LLM tailored for resource-constrained environments. Section: Experiments. In this section, we conduct experiments to evaluate the effectiveness of our LEGO methodology by addressing several key questions. First, we explore whether combining task-independent data and client-distributed SLMs can produce a strong LLM. Next, we investigate the impact of fine-tuning each client SLM with task-dependent data. Lastly, we assess if LEGO allows for the stacking of differently shaped blocks. We follow a specific workflow for our experiments. Initially, we prune an LLM to create smaller SLMs, which we then set up as client models. Each client model is fine-tuned using its local data, and we aggregate these models to form a global update. This update is applied to a global model with no sparsity and to the client models, which we then evaluate. We compare LEGO against two baselines. One is a global model produced by Fedit using 4 Llama 7B client models fine-tuned on independent and identically distributed data, representing an ideal scenario. The other baseline consists of a global model from 8 task-specific Llama 7B client models, each fine-tuned on a different domain from the Databricks DALI 15K dataset. For all LEGO experiments, we utilize our heat ag method to aggregate client weights, which accounts for their differences, unlike the simple averaging used in FED-AVG. Since heat ag has the same computational cost as FED-AVG, any speed improvements in LEGO stem directly from model pruning. We observe up to a 1.6 times speedup in inference and a 1.4 times speedup in fine-tuning with sparse GPT-produced SLMs compared to models with no sparsity. As pruning methods advance, we expect LEGO to achieve even greater speedups. In our first experiment with task-independent data, we fine-tune smaller models individually, treating them as subunits that we later combine to create a final LLM. We prune an LLM to generate 4 SLMs with 75% sparsity, using independent and identically distributed client data. Each client dataset is divided into 4 segments, ensuring they cover the same domains in equal proportions. In each round, one client fine-tunes its model on local data, which is then aggregated with the global model. The results show that LEGO matches FEDIT's accuracy on the recombined global LLM, despite only fine-tuning a fraction of the parameters. In the second experiment, we assess knowledge transfer in a task-dependent scenario with non-I-D data. We use 8 SLMs, each with 75% sparsity, and divide the Databricks DALL-E 15K dataset into 8 domain areas. Each client model fine-tunes on one specific segment, leading to varying amounts of local data. Similar to the previous experiment, each client fine-tunes on its data and aggregates with the global LLM. The results indicate that LEGO outperforms FEDIT, achieving an accuracy of 0.571 compared to 0.563, demonstrating effective knowledge transfer among models despite their different tasks. Finally, we evaluate how non-I-D data affects the quality of global updates produced by LEGO. We monitor the performance of client SLMs over time, assessing their average performance after each global update. Our findings reveal that client SLM performance improves almost linearly after each update, even when local data sizes vary significantly. This suggests that SLMs can effectively capture knowledge from limited data, mitigating the challenges posed by data heterogeneity. Section Summary. In this section, we conduct experiments to evaluate our LEGO methodology by examining the robustness of recombined SLMs from task-independent and task-dependent data, demonstrating that our approach achieves comparable or superior accuracy to baseline methods while significantly improving inference and fine-tuning speed. Our results indicate that LEGO effectively facilitates knowledge transfer among heterogeneous client models, leading to enhanced performance in global updates despite varying local data sizes. Section: Combining differently shaped blocks. In this section, we explore how differently shaped blocks can be combined, similar to how not all SLMs are the same size or shape. The key requirement is that they must be able to stack together, much like LEGO blocks. We illustrate this by showing how 3 blocks of different shapes can merge to form a larger block. This concept applies to SLMs as well, where each can handle various tasks or levels of sparsity, and when combined, they create a strong LLM that addresses the diverse tasks of its components. Our earlier findings indicate that knowledge can be transferred between SLMs that are fine-tuned with either task-independent or task-dependent data. Here, we investigate whether this knowledge transfer also happens between SLMs of different shapes and sizes. We set up a federated learning environment with 4 client SLMs, each having a different sparsity level: 0%, 25%, 50%, and 75%. All SLMs, including the 0% sparsity model, LLM, are fine-tuned on their local data, which comes from equal segments of the Databricks DALL-E 15K dataset. We first fine-tune all client models and then perform a single round of aggregation, applying the global updates uniformly across all models. We present the performance of these models at 3 stages: after initial pruning, after fine-tuning, and after global updates. Our results show that fine-tuning enhances performance for all model sizes, with the most significant improvement seen in the 75% sparsity model. However, during aggregation, the performance of all models improves except for the 75% sparsity model, which likely suffers due to its smaller size. Previous research suggests that smaller models can learn better, creating stronger representations, but during aggregation, their learned representation can be diluted by larger models. When we compare our results to the FEDIT baselines, we find that our heterogeneous models still produce a robust aggregated 0% sparsity LLM, indicating successful knowledge transfer. This shows that LEGO allows for flexible model selection, enabling knowledge transfer between models of different sizes and adapting to device capabilities. To further analyze knowledge transfer, we repeat the experiment 4 times, each time leaving out one client model from the aggregation. We observe that the performance of the 0% and 50% sparsity models declines when the 75% sparsity model is excluded. This confirms that smaller models can effectively transfer knowledge to larger models, although the 75% model consistently shows performance degradation during aggregation. From these results, we draw two conclusions. Smaller models contribute more significantly to the 0% sparsity LLM, and larger models are less effective at transferring knowledge to smaller models. While our experiments indicate potential for improved performance in heterogeneous settings, they also show that our results are comparable to the federated baselines, suggesting that LEGO models can outperform homogeneous models. In terms of related work, we note that research on heterogeneous federated learning with pre-trained language models is limited. We discuss the significance of this context in the appendix. The first comprehensive study on model-agnostic federated learning was Inclusive FL, which examined layer-pruned BERT models. They found that layer pruning had minimal impact on BERT's performance, a finding that does not hold for modern LLMs due to the distribution of large features across layers. We also consider approaches focused on layer selection tested only on encoder-style LLMs, which overlook large features. Our work contrasts with traditional federated learning methods like FEDIT, which uses FED-AVG for aggregation but struggles with heterogeneous models. Recent literature has begun to address heterogeneous LoRa ranks in federated learning, but these methods often assume model homogeneity, limiting their effectiveness. In LEGO, we enable larger models to operate on more powerful devices while allowing smaller models to function on weaker ones. Our aggregation technique does not require creating full-sized weights for every client model, making it more scalable than methods like Flex LoRa, which relies on resource-intensive operations. We utilize the standard sparse GPT pruning technique for our experiments, but LEGO is compatible with various pruning methods, preserving sparsity patterns in client models. To our knowledge, our work is the first to leverage pruned decoder-style LLMs for federated learning, facilitating speed improvements for client models while scaling down to match client capabilities.